Alright, welcome to day 2 of NTI. At this point you should probably pause your video and make sure that you have a piece of paper and something to write with. At the top of your paper, make sure that you write down the title. We're looking at Spring Semester Day 2, Factoring Methods. Some of what we're going to do today will be review, but some of it will be brand new to you. Remember also that you should be writing down everything you see on these slides unless I tell you otherwise. At this point on the opening slide, all you need to write down is the title. These are just examples of the kinds of things we'll be factoring, but make sure you write down the title. The next slide you do not need to write down. It shows our learning targets. We are going to be using or learning 4 different methods of factoring today. The greatest common factor, factoring by grouping, difference of two squares, and a plain x squared trinomial, or factoring a quadratic trinomial when a is equal to 1. We'll look at AC method next time. All right. Again, on your piece of paper, you want to be writing down the title at the top of the slide, which says method number 1, greatest common factor. You also want to write down the directions that are on this slide. Some of you didn't do that yesterday, so please make sure you do it today. And then you want to write down the original expressions. You want to write down numbers 1, 2, 3, and 4, and the original expressions that are there. Feel free to pause if you need to do that. Greatest common factor involves looking at whatever terms are provided to you and asking, what is the greatest value or expression that I can divide out of each of these evenly? I look at the coefficients first, 27, 63, and 63. The greatest common factor there is 9. Then I look at k to the 9th, k to the 4th, and k to the 3rd. That means I can factor out 3 k's, so k to the 3rd. When I divide that out, I'm left with 3k to the 6th, right? Because if I multiply back, 9 times 3 is 27. K to the 3rd times k to the 6th gives me k to the 9th. Then continuing on, 63 divided by 9 gives me 7. I've divided out 3 k's, so there's 1 left. And then finally right here, it's just going to be plus 7, since 9 times 3 is 63, and k to the 3rd comes along for the ride. That is our factored form of the original expression. As we look at this next one, I see coefficients of -5, 20, 15, and -45. So obviously our greatest common factor is going to be a 5. I can also factor out a single b. Now, it's usually customary to factor in order of the term with the highest exponent to the term with the lowest exponent. So I'm going to begin by factoring out of this term. If I factor out 5b from this, I'll be left with 4b to the 3rd. Then I'm going to move on to this term, right, since that has b to the 3rd. If I factor out 5b, I'll be left with -9b squared. Then I'm going to move on to this term here. If I factor out 5b, I'll have 3b. And then finally, if I divide -5b by 5b, I'm just left with a -1. So there's our factored form of that expression. Keep in mind, factoring is just like breaking things up into its smaller parts. As we look at number 3, I can see coefficients of -40 and -16. That gives us a greatest common factor of 8. However, you may notice that our leading term has a coefficient that is negative, so that means I'm also going to factor out the -1. So let's factor out a -8 as well as 3 v's. If I do that, I factor out -40 divided by -8 gives me +5, and if I factor out 3 of the v's, I'm going to be left with 3 v's in here. Then if I factor -8 out of -16, I'll have +2, and I already factored out all 3 v's, so I close the parentheses, and here is our factored form right there. Finally, as we look at number 4, our greatest common factor appears to be 8a squared. And if we factor that out, we'll be left with 10a to the 6th minus a plus 1, right? Since -a times this would give you -8a to the 3rd, and then times 1 or plus 1 at the end, since 8a squared times 1 is 8a squared. All right, that should mainly be review. Let's now look at a few methods that might not be ones that you've seen before. Let's look at method number 2. On your page, you want to make sure you've written down method number 2, factor by grouping. You want to make sure you've written down the directions as well as each of the questions themselves. An important thing to know about grouping is, typically grouping is done when GCF doesn't work. And there are 4 terms. So I can tell in each of these examples that there are 4 terms. Let's try GCF. 6, -5, 24, and -20. There is no greatest common factor of those terms, and there are 4 terms. So here's how it works. If you notice there's no greatest common factor, but there are 4 terms, imagine drawing a line. Well, don't just imagine, actually do it. Let's draw a line here, and let's figure out the greatest common factor on the left-hand side. These 2 terms. In these 2 terms, the greatest common factor, there's nothing between 6 and -5, but they do have 2 p's in common. We can factor out p squared, which would leave us with 6p minus 5. Now on the right-hand side, we want to do the exact same thing. What I mean is, we want to have 6p minus 5 in the parentheses. We want these 2 to match. So the question becomes, let's work backwards. If I want 6p minus 5 in the parentheses, what do I need to divide these both by? Well, we would need to divide them by 4, right? And you'll notice what we've done is we factored p squared out of the left-hand side, we factored 4 out of the right-hand side, and they're both being multiplied by 6p minus 5. What that means is that this can be rewritten as 2 binomials. You can essentially put these 2 pieces together into a single binomial. P squared plus 4 is being multiplied by 6p minus 5. This is the factored form of what we started with. Let's try it with another example. Again, you'll notice there is no greatest common factor of all 4 terms, so we'll draw a line in the middle. On the left-hand side, we can factor out 5r squared, which will leave us with r plus 3. On the right-hand side, we know we want an r plus 3 in the parentheses so that these match. In order to get there, we need to divide both of these terms by an 8, or a positive 8. Then to wrap things up, we can group together these 2 terms here, the 5r squared and the 8, into a single binomial like this. 5r squared plus 8 is multiplied by r plus 3, and there is the factored form of our original expression. All right, moving on to method 3. As you write down on your page, you want to write down method 3, difference of 2 squares. You want to write out the directions that say factor each completely. And you want to write down the original problems here for 7, 8, 9, and 10. Again, feel free to pause the video if you need to. Now, difference of 2 squares is really just recognizing a pattern. So here's what I'm going to do. I'm just going to show you the answer and see if you can piece together where it came from. If you see a squared minus 5, the factored form of this is a plus 5, a minus 5. Let's think about how we know that's true. Well, first thing, if I wanted to work backwards, if I wanted to get from this to this, I would use distributive property, wouldn't I? Specifically, I would use FOIL, right? Factoring is just reverse FOIL. Remember, F stands for first. A times A is A squared. And then I get minus 5A, and then I get plus 5A, and then I get minus 25. Do you notice what happened with those 2 middle terms? Negative 5A and positive 5A cancel each other out, leaving you with A squared minus 25. So here's what that tells you. When you see a difference of 2 squares, you might be wondering, how do I know it's a difference of 2 squares? Well, let's decode it. Difference means subtraction. Squares mean perfect squares, right? The difference of 2 perfect squares. A squared is a perfect square. 25 is a perfect square. If you see the difference of 2 squares, you will factor it like this, what I have boxed in. The square root of the first term goes in the first position here and the first position here. The square root of the second term goes in this second position here and second position here. And the only difference between the 2 expressions is that one of them has a positive sign and one has a negative sign. Let's try another one. As we look at number 8, is 4x squared a perfect square? Sure. Is 1 a perfect square? Yes, it is. So we can factor this out like so. What's the square root of 4x squared? Well, the square root of 4 is 2. The square root of x squared is x. So we have 2x in this first position. What's the square root of 1? It's 1. So we put 1 in the second position. And then we just need to make sure we have opposite signs here. 2x plus 1, 2x minus 1. There is our factored form. As we look at number 9, right, you'll notice that those are perfect squares. You could factor them as such, right? The square root of 36a squared is 6a. Square root of 16 is 4. And we have a plus and we have a minus. The thing is, though, that is not in fully factored form. And here's why. You'll notice that back when we began factoring, the very first method we looked at was greatest common factor. You should always check to see if there's a greatest common factor. And if there is, factor that out first. So as I look at 36 and 16, I notice that I can divide both of those by 4. So let's do that. Let's divide by 4, leaving us with 9a squared minus 4. Now I'm going to continue factoring. The 4 on the outside stays there, and I see a difference of 2 squares, right? 9a squared, square root there is going to be 3a. Square root of 4 is 2. One has a plus, and one has a minus. And there is our factored form. Before, when we factored this, I'll just write it out to the side, right? We had 6a minus, or plus 4 and 6a minus 4. While that's close, well, I mean, it's equivalent, it's not fully factored. In this first expression, we could have factored out a 2, leaving us with 3a plus 2. And then in the second expression, we could have factored out another 2, leaving us with 3a minus 2. And you can see how 2 times 2 would give us that 4 in front. So might as well just go ahead and factor out the greatest common factor first. In number 10, you can definitely tell you should factor out a greatest common factor because 50 and 2 aren't perfect squares. Let's factor out a 2. Leaving us with 25x squared minus 1. And now I can see 25 and 1 are perfect squares. So we're going to factor this out. The square root of 25 is 5, so that's 5x and 5x. Square root of 1 is 1. And we have a plus here and a minus here. Here's our fully factored form. All right, to wrap things up, we're going to look at method 4. So make sure once again that you have written down the title of method 4 up at the top. Make sure that you've written down the directions here and that you've written down each of the 4 examples that are listed here. So let's begin with number 11. Now I call these plain x squared trinomials. They're also, another way to talk about them are quadratic trinomials where a is equal to 1. We've done a little bit of factoring with these throughout the semester, but I want to remind you. In order to figure out how this is factored, first, I know that this is going to begin with an n, and this is going to begin with an n. N times n is n squared. The question is what number goes here and what number goes here. And so for that, I use what I call my blank system. I know that I'm looking for 2 mystery numbers. Those 2 mystery numbers should multiply to give me -5. Those same 2 numbers should add up to give me +4. So make sure you've written these blanks out to the side. That's what happens when you do first the outer and the inner pieces get added together to give us 4 in the middle. And then the L of FOIL, right, is what gives us that -5 at the end. So we're looking for 2 numbers that multiply to give us -5 and add up to give us +4. Well, that would be 5 and -1, wouldn't it? 5 times -1 is -5. 5 plus -1 is 4. So we can write this as n plus 5, n minus 1. There's our factored form right there. Let's practice another one. Let's use our blanks method here. We are looking for 2 numbers that multiply to give us -40 and 2 numbers that add up to give us -6. So let's consider what those numbers might be. Well, there's a variety of numbers that might work. You could try like 8 and 5, though that's not going to work, but it looks like 10 and 4. Some combination of 10 and 4 is going to work. What's important is that when we add them up, we get -6. So it's got to be -10 plus 4, right? That gives us -6, and -10 times 4 gives us -40. So that means this factors out into m minus 10, m plus 4. If at any point you doubt your answer, try using FOIL. First, outer, inner, last, and you should get back to your original. Now, as we look at numbers 13 and 14, you might be thinking, how are these plain x squared trinomials? How is a equal to 1 in numbers 13 and 14? A being the leading coefficient. Well, you're right. The leading coefficient in each of these is not equal to 1. However, remember that lesson I showed you earlier, and that was try greatest common factor first. As I look at these three terms, I notice that I can factor a 2 out of all of them, leaving us with x squared minus 6x plus 8. The same is true in number 14. We can factor a 5 out of everything, leaving us with n squared plus 9n plus 8. And now we can move forward with our factoring methods, right? As we look at this right here, I'm looking for two numbers that multiply to give us 8 and two numbers that add up to give us -6. Well, what would those two numbers be? Let's see, that would probably be -4 and -2. Right, -4 times -2 gives us +8, and -4 minus 2 gives us -6. So we still have that 2 out in front, and then x minus 4 and x minus 2. There's our fully factored form for number 13. And then in this one, we'll use our blanks method, right? Blank times blank equals 8. Blank plus blank equals 9. Well, 8 times 1 is 8. 8 plus 1 is 9. So we keep the 5 in front. We already factored that out. And we have n plus 8 and then n plus 1. All right, thanks for watching. Make sure you've got all those steps copied, and have a great day.